Hi everybody, welcome back. In this video we're going to pick up where we left off on our last video about ordinary least squares. Last time we talked about the ordinary least squares assumptions. I talked a little bit about some of the violations of those assumptions, but we're going to go into a little bit more detail here. So again, 5 OLS assumptions. We're going to talk about each of them and what happens when they're violated or how they might be violated. And then we're also going to kind of talk about, to a certain degree, how big a deal they are. And I'm going to be using this abbreviation NBD for no big deal. And it's not that they're not a big deal at all, but a lot of these assumptions, when they're violated, we can do things to resolve them pretty easily. The last one, which if you recall was no endogeneity, that one's going to be the bigger deal out of all of them. And so relative to endogeneity, we can fix them. But yeah, we'll just go through them, and I'll kind of talk about briefly on the types of things that we can do to address them, and then through future videos, the actual mechanisms and tools that we use to address some of these violations of the assumptions. We'll go into more detail there. Okay, but first, remember our first OLS assumption was normality of mean zero of the error term. Okay, and this one is no big deal because the inclusion of the constant term, beta 0, helps ensure mean 0 in the error. And so we want the error term to be normally distributed with mean 0. By including the constant term, that's gonna help ensure that's the case. And it becomes more normal as the sample size increases. Right, and that's going to be due to the law of large numbers and the central limit theorem. We talked a little bit about those, but going back to statistics, if you look into that, you see that as the sample size increases, law of large numbers kicks in, and central limit theorem to create normality will kick in as well. Okay, that was it for the first one. The second assumption was no autocorrelation. That is the correlation between the error terms of the different points in the data. Again, this one is more or less no big deal. It is problematic in time series data, as I discussed in the last video, right? Because what happens in time period 1 is correlated with what happens in time period 2. What happens today is going to affect what happens tomorrow. We also talked about how you can have autocorrelation spatially, spatial autocorrelation with things like home prices being a factor, being correlated with neighbors' home prices. But we have special tools to deal with this, time series tools, time series statistics. And so, again, that's something that there are entire courses on time series econometrics. So that's something we may touch on here in the next month or so, but if not, that time series econometrics gets more into prediction rather than causal estimation. So that's not too much of an issue with cross-sectional data. Okay, the problem with autocorrelation, if there's a violation, is that it's going to increase the variance of the betas. That is the regression coefficients. So it'll increase the variance, but they won't be biased. And so essentially what's going to happen there is that the beta hats. So what might happen there is that a beta hat might look significant, when it actually isn't. Okay, but the variable won't be biased, however, and so a biased variable is going to have a much bigger problem than some problem with the standard errors and the significance. So in general, that one's also not too big a deal, especially for cross-sectional data, the type of data that we'll be working with. Okay, next assumption is that there's no heteroskedasticity. And remember, so I showed it in the last video, but I'll just do it again here really quickly. I'll show homoskedastic errors and heteroskedastic errors in two graphs to show you the difference. Heteroskedastic. Okay, and so if you have some data that's pretty evenly dispersed between the x and y for all levels of x, whether it's here, whether it's here, or whether it's here. If you were to draw the variance of that data, it has about the same variance all the way along. And so, I mean, you can still have your regression line going through there like that, but the variance of the data is the same no matter the value of x. But again, if you had something here like some x being age or income, and y maybe being something like food consumption or health is another good example. Where, and if this is age, there are, as people are younger, they're generally a lot healthier, and most people are going to be clustered into actually high levels of health. There will be some people down here with not as great health, but most people have very high levels of health, right? And then across time, you're still going to have, okay, you're 20, now you're 30, and then so on, and then up, you're 70 all of a sudden. There's still going to be some healthy people in their 30s, but they're going to start, start winding down a little bit, and then in the 40s and so on and so forth. And then in the 70s and 80s, there's going to be still some healthy people up here, but there's going to be a lot more unhealthy people too. And so let me just get some more data on here. And so, yeah, so the variance here in the 20s is going to be, quite tight with just a couple outliers there. But then as you move on, the variance is going to grow, and then the variance is going to grow even more. And so you have this fanning out of the data. That's heteroskedastic errors. And so if you have data that violates that, then you have heteroskedasticity. Fortunately, this is also no big deal, because you can use robust standard errors which correct for heteroskedasticity, where, so, here, just to finalize this, some small errors at low levels of x, and small standard errors, estimated errors, and at high levels of x, you have high standard errors at high levels of x, because you get a lot more variation. Okay, so, but again, not too big a deal because we can use robust standard errors. A lot of statistical packages easily fix these in regression software. It'll sometimes be an option, or it'll oftentimes just be automatic. So your robust standard errors are going to correct for this difference in the variations across time. Well, across x, whatever x is. The problems with that is that it increases the variance of the betas again, but again, it does not bias the betas, and it'll end up underestimating the standard errors of the betas if you don't correct for it. But if you correct for it, then that'll solve the problems. So that's what we've got going on there. Number 4 is no perfect multicollinearity. Remember, this is when x variables are correlated with each other. And so just to give another example of that here, so if y was equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus the error, but suppose that x2 is a linear combination of x1. It's just 2 times x1. Then we have y would be equal to beta 0 plus beta 1 x1 plus beta 2 2x1 plus the error term. And so then ultimately, if you tried to run this original equation, it's trying to capture one effect, or one variable here ultimately, but there are 2 effects, and so that's going to be that'll cause some problems. In general, though, it's not a big deal because again, the problem that it's going to cause is the same as the others. The variance of the betas increases. It does not bias the betas. And the solution, one possible solution, is that we could drop the collinear variable. And in this case up above, that would be x2. And we should, for a perfectly collinear variable, but usually we do nothing. So when you have multicollinearity, especially for causal econometrics, if you are including variables in your equation, you should be doing it for a purpose. And even if two variables are multicollinear with each other, so for example, if we're modeling sales in a firm and we're modeling it using some macroeconomic variables, let's say unemployment, the unemployment rate, and income. Well, unemployment and income are correlated. If you're unemployed, your income is going to be lower. Or in general, like if a town's unemployment rate is lower, that town's income per capita is going to be lower. So these are definitely multicollinear with each other to a certain degree. But if there's reason to believe that unemployment contributes to sales and income contributes to sales, you should definitely leave those in the model. Because yes, you might have some problems with the variance of your betas increasing, but that's not as big a deal as having a biased estimator. So if beta 2 or beta 1 is biased, it's going to look like your unemployment causes a different level of sales than it actually does, or income causes a different level of sales than it actually does. So if you're trying to do causal econometrics, even if there's some multicollinearity in there, leave it in there, because especially as the sample size increases, it's going to get better. But if you take it out, you're going to have an omitted variable bias, which I'm going to have an entire video on next. But let's write a couple things down about this. We could drop one variable, but if it should be included in the model, we would then have, that is, if we dropped it, we would then have omitted variable bias. Which is a bigger problem than multicollinearity. Okay, and omitted variable bias, okay, well, yeah, omitted variable bias is one of the sources of a violation of our next and last assumption, which is no endogeneity. Okay, and if you have endogeneity, which could come from omitted variable bias or simultaneous equations, then your beta, your estimate, is going to be biased. And so I guess I'll stop there for multicollinearity. A lot of people talk about multicollinearity because it's a very common problem. There are a lot of variables that are related to each other. It's just the nature of how especially social sciences work. Multicollinearity is not as big a deal as most people make it out to be. So yes, there's going to be multicollinearity. Do you need to worry much about it, especially for causal econometrics? No. Because if there should be a variable in there, you need to keep that variable in the model. Okay, and so let me explain part of the last reason why endogeneity, and then in the next video, I'll do an entire video just on some of the sources of endogeneity. So remember, endogeneity is when the error term is correlated with one of the x variables. And this one is a big deal. And so this is the only one of the 5 that's really the biggest deal of them all, and that's because it leads to biased estimates of beta, right? And so what that's going to be looking like here, is if we think we have some relationship and we think that beta is here, that's our estimate of beta, well, it could be that the true underlying distribution of beta is here. And so it could be the case that, well, maybe this here is 0, and this is 1, and this is 2. And so you say, oh, there's a 1-to-1 relationship between x and y, but actually there's a 2-to-1 relationship. Well, you're off by, double. An even bigger problem is if 0 is somewhere in here. And you're saying, oh, look, there's a negative relationship. It's less than 0. There's a negative relationship in the variable between x and y, but actually there's a positive relationship. And so if you have a biased estimate, this is a totally possible and common phenomenon. So you don't want, we're trying as best as we can to eliminate biased regression coefficients. That's like the same thing as saying, like we talked about, if you have some variable, some relationship here between x and y, well, the other source of bias we talked about previously is if you omit the beta 0 term. That would mean that you're starting at the origin. Here's the real relationship. You're estimating a much stronger relationship. That's the same thing that could happen with a beta, with some endogeneity or omitted variable bias. You might even have the beta 0 correct. Forget about leaving it out of the equation. Maybe your beta 0 is correct, but you might still have the wrong biased estimate, the slope of beta 1. And so again, or it could be negative, your estimate. It could be beta 1, like this. So positive real true one, negative estimated relationship. And so that's why endogeneity is such a concern among causal econometrics, among policy analysis, because if you're putting a policy into place and you're or a business decision into place and you're saying, hey, if we put this advertising campaign into effect, it's going to increase our sales by 5 times. Well, if you have a biased, and then you have to pay some money to put the advertising campaign out. Well, if you're wrong and your estimate is biased and it's actually 0.5 times, well, you might have just lost a whole bunch of money for your company. Or you might have put a policy into place that is going to do the opposite of what you were trying to do. So, so endogeneity is a big deal in econometrics, and this is what we want to address most of all. So let's see. If the error term and some x variable are correlated, the OLS estimates will likely attribute to x right, through the beta effect, it will likely attribute to X some of the variation in Y that actually comes from the error term. Okay, epsilon. And so hopefully I've convinced you that endogeneity is a big deal. I'm going to stop the video here, and in the next, we're going to look at sources of endogeneity and talk a little bit about that, which is going to be coming from the omitted variable bias and from simultaneous equations. Okay, so we're going to leave it off here. Thank you for watching, and I will see you in the next video.